from our function z. Z equals f of xy. If we consider the partitions, we see that for any x between 0 and 4, we could have an x interval, and our y interval would then run from here to here, from the x-axis out to this curve. This curve occurs in the xy plane where z is 0, so that on this curve x squared plus y squared equals 16. For a given value of x, then, y will run from 0 out to this curve, the y value being square root of 16 minus x squared. Again, we can form a summation corresponding to the ij partitions, the x running from x naught to xn, the y from y naught to y sub m, where the m depends on just where x is, but the result is going to be then an integral from 0 to 4 with respect to x, and with respect to y from 0 to the square root of 16 minus x squared, and it's simply going to be the integral of this area ratio. The delta y delta x will be the area down in the xy plane. Multiplied by this ratio, we get the area of the region on the surface of our sphere, so that this is going to be the square root of 1 plus fx squared plus fy squared. All we need to do to get our final integral is figure out fx and fy, and that's fairly easy. For example, fx is going to equal what? Well, it's going to equal the x derivative of our inner function. We have to use the chain rule, so that's 16 minus x squared minus y squared with respect to x, and then it's times the derivative of a square root function, and a square root of u, for example, has derivative with respect to u of 1 over 2 times the square root of u. So that'll be 1 over 2 times the square root of 16 minus x squared minus y squared. The x derivative of this expression is not just negative 2x, and that'll be times 1 over 2 times the square root of 16 minus x squared minus y squared. And our final expression for fx is then just negative x over square root of 16 minus x squared minus y squared. Very analogously, our y derivative is calculated. Not going to go through the details of that because x and y are both appear in the expression in exactly the same form. We're just going to get negative y over the square root of 16 minus x squared minus y squared. So that our expression square root of 1 plus fx squared plus fy squared is just equal to the square root of 1 plus x squared over 16 minus x squared minus y squared plus y squared over 16 minus x squared minus y squared. And we might as well put all this over common denominator. So that's going to be the square root of 16 minus x squared minus y squared plus x squared plus y squared divided by 16 minus x squared minus y squared. And that simply comes out square root of 16. The x's and squareds and y squareds add up to 0. So we have the square root of 16 over the square root of 16 minus x squared minus y squared, and that's just going to be 4 over the square root of 16 minus x squared minus y squared. Now, just to think briefly about this expression, this is the area ratio. That's the ratio of the area above the region of the xy plane to the area of the xy plane. That area ratio has to be greater than or equal to 1, because you can't have less area above the region than you have in the region. If the region above is at an angle with respect to the region below, then you can have an area ratio greater than 1, but you can't have less area above than you have in the xy plane. So we stop for a second to verify that this is always greater than or equal to 1. The denominator is at most the square root of 16, because we're subtracting two positive quantities from 16. Square root of 16 is 4. That would give us area 1. Any number less than 16 under the square root is going to give us a number less than 4, giving us an area ratio of greater than 1. So we can say that's okay. So we can proceed to set up our integral. Okay, remembering that this is 4 over the square root of 16 minus x squared minus y squared, we can write down our integral. Let's just do it here. It's the integral from 0 to 4 of the integral from 0 to the square root of 16 minus x squared of 4 over the square root of 16 minus x squared minus y squared, and that's dy dx. To perform this integral, we have two choices. We can integrate by trigonometric substitution, which might seem like a bit of a pain here, but it really is not particularly difficult. We'll do that in a minute. Or we can started to write down the wrong letter there. We can switch to polar coordinates. So we can do one and or the other. We might want to switch to polar coordinates because, of course, x squared plus y squared is just r squared. So let's explore that possibility first, and then we'll come back and look at the trigonometric substitution.